Hi, this video will be about the modulation property of the Fourier transform. This property is also known as the multiplication property because it is related to the Fourier transform of the product of two signals. Okay, the property can be stated as follows. Okay, consider two signals x1 of t and x2 of t with the corresponding Fourier transforms. x1 of t has the Fourier transform x1 of omega, and x2 of t has the Fourier transform x2 of omega. Then the multiplication property tells us the following. The product of x1 of t and x2 of t will have the Fourier transform which is equal to 1 over 2 pi x1 of omega convolved with x2 of omega. So again, the multiplication operation in time domain corresponds to a convolution operation in frequency domain. Well, we immediately note that this is related to the convolution property by duality. So convolution property and multiplication property are dual properties of the Fourier transform. Convolution in time domain corresponds to multiplication in frequency domain, and multiplication in time domain corresponds to convolution in frequency domain. Now let us see the proof of this fact. The proof is quite straightforward. We just write down the Fourier transform of the product of x1 and x2. So it is from minus infinity to plus infinity, x1 of t, x2 of t, e to minus j omega t integrated with respect to t. Then we write this as follows. From minus infinity to plus infinity, x1 of t. Okay, we can express x2 of t by means of the inverse Fourier transform relation. So it is 1 over 2 pi from minus infinity to plus infinity. x2 of, okay, since we have omega as well in the original expression, let us use a different variable. Let us use omega prime. x2 of omega prime e to j omega prime t d omega prime. So we have this as x2 of t e to minus j omega t integrated with respect to t. Then interchange the two integration operations. Okay, so we have from minus infinity to plus infinity x2 of omega prime. Okay, we can write 1 over 2 pi as the constant term multiplier. We can take it outside the integral, 1 over 2 pi. And then we have from minus infinity to plus infinity x1 of t e to minus j omega minus omega prime t integrated with respect to t. So we have interchanged the order of integration, and then we have the omega prime. But we recognize this term as the term here, the expression from minus infinity to plus infinity x1 of t e to minus j omega minus omega prime t integrated with respect to t as the Fourier transform of x1 of t evaluated at omega minus omega prime. So we recognize the integral. Okay, let us write it once more. 1 over 2 pi from minus infinity to plus infinity x2 of omega prime x1 of omega minus omega prime d omega prime, but we recognize the integral as the convolution integral. It's the convolution of, remember, convolution is commutative, therefore we can express this as x1 of omega convolved with x2 of omega, or x2 of omega convolved with x1 of omega. Convolution is commutative, so both will yield the same result. So this is the proof of the multiplication property. Now let us see an example, and this is a rather important example because it is sometimes known as the frequency shift property. So let us write it here, frequency shift property, but it is only an application of modulation property. Okay. We have supposed that we have the Fourier transform pair, a certain signal and its Fourier transform x of t and x of omega. So let y of t be x of t multiplied by e to j omega 0 t. So what is the Fourier transform of y of t? By modulation property, y of omega is equal to 1 over 2 pi x of omega convolved with Fourier transform of e to j omega 0 t. And what is the Fourier transform of the complex exponential signal e to j omega 0 t? It is 2 pi delta of omega minus omega 0. Remember, Fourier transform is a measure of the frequency content of a signal. In e to j omega 0 t, the frequency omega 0, the frequency component omega 0 is present with infinite magnitude, and all other frequencies are not contained. So 2 pi's will cancel out, and y of omega therefore will be equal to, now the convolution of x of omega with the impulse is, remember, x of omega minus omega 0. So as the name implies, we have a frequency shift. If the Fourier transform of the signal x of t is x of omega, when you multiply x of t by the complex exponential signal e to j omega 0 t, all frequency components are shifted by an amount equal to omega 0. Okay. Now let us see another example related to this property. The next example related to the multiplication property will be the following. This is also quite interesting. Show that sinc of omega over 2 pi is equal to 1 over 2 pi sinc omega over 2 pi convolved with sinc omega over 2 pi. Now this expression seems to be an expression quite difficult to understand at first sight, but we remember the following. Okay, how can we show or prove this? Of course, we are not going to use convolution of the sinc function with itself to prove that it is again related to itself with only a constant multiplier equal to 1 over 2 pi. But we are going to do the following. We are going to use the multiplication property to prove this, the validity of this statement. Now remember that a Fourier transform of the rectangular pulse rect t is equal to sinc omega over 2 pi. Okay? But we know that rect signal is just equal to 1 for t between minus 1/2 and 1/2. As you remember, you can put equalities as well. Makes no difference in the result. And 0 otherwise. Okay. And we note that rect t is equal to rect t multiplied by itself. When we multiply rect t with itself, we obtain rect t again. So, we can take the Fourier transform of both sides and we obtain the result. Now, Fourier transform of rect t is sinc omega over 2 pi, and Fourier transform of rect t times rect t is 1 over 2 pi. The Fourier transform of rect t convolved with itself. Sinc omega over 2 pi convolved with sinc omega over 2 pi. So we get the result. Okay. Let us call this equation 1, this equation 2 and this equation 3. So substitute 2 and 3 in 1 and we obtain the result. Okay, so this is also a quite interesting application of the modulation property. A seemingly difficult expression can be analyzed very easily by using the modulation property or multiplication property. Thanks for watching.